Hi, and welcome back. We're up to Lecture 5, Segment 2. And in this segment, we're going to walk through the mathematical calculations of the correlation coefficient little r. So when it comes to the important topics for this segment, that's about it. Just knowing how to do this calculation. I'm going to show you two different ways to do it. One I refer to as the raw score formula, and the other I refer to as the z-score formula. But in the end, I'll show you that they're equivalent. There's actually just one new concept here. There's a lot of math that's going to come at you in this segment. The one new concept is sum of cross products and covariance. And I'll illustrate that through the calculations. So first, this is more of a conceptual presentation of the formula, not a mathematical presentation. But just conceptually, what little r is, what the correlation is it's the degree to which x and y vary together relative to the degree to which x and y vary independently. So we could rewrite that down below as the covariance of x and y, and again, I'll get to that when we do the calculations, over the variance of x and the variance of y. And as I mentioned, there are two ways. There's more than two ways. I'm just going to show you two: the raw score formula and the z-score formula. We'll start with the raw score formula. To illustrate this, it's actually really easy if you followed along in Lecture 4 and the calculation of summary statistics, particularly the calculation of variance. So remember, variance is equal to standard deviation squared. Another way that we write that is mean squares, because it's the sum of squares over n, or the average sum of squares. Mean squares is variance. It's also standard deviation squared. Let's review the calculation of variance from that Lecture 4. Remember, I used the example of Jeremy Lin. This was the Linsanity thing that swept New York during the NBA season, not this year, the year prior. And I use this to illustrate not only how many points per game was Jeremy Lin averaging during those 10 games, but what was his variability. So remember, we calculated the mean, we calculated the standard deviation, we calculated the variance. The way we did that is I listed out the points per game across 10 games, and then that first column, points per game, to get the mean, we just sum that column and divide by the number of games. So it's the sum of x divided by n. That's just the average. So during those 10 games, Jeremy Lin was averaging 22.7 points per game. To calculate variance, we then have to look at each individual game and see how much is he differing from his average. So this middle column is what we call deviation scores. We just take points per game for that one row and subtract out his mean. So the first one is 28 minus the mean, 22.7, which is 5.3. We go down and do that for each row. We can't sum and take the average of the deviation scores because they sum to 0. So the average would be 0. So to fix that problem, we just square all the deviation scores, and that's the third column, right? So then we square every deviation score, sum those, and that's that phrase, sums of squares. It's going to be a really important concept going forward throughout the course. This number down here, sums of squares, is 922 divided by 10, because there were 10 games. That gives me mean squares. That's variance. So to summarize the results, his mean, or average points per game during that time, was 22.7. His variance, or mean squares, was 92.21. That's not that meaningful of a number, so let's take the square root of that to get us back into the units of points per game. That's the standard deviation. He was deviating on average about 9.6. Remember, that's a little inflated because I included that one game where he scored just 2 points. He didn't start. Remember, back in Lecture 4, we eliminated that and his standard deviation was a little lower. But that's the calculation of variance and sums of squares. To calculate a correlation coefficient, all we have to do is add that one new concept, sum of cross products, and then covariance. So to review, how did we get sums of squares? For each row in that data frame, we calculated the deviation score. Then we squared each deviation score, then we summed them, sums of squares. To calculate sum of cross products, remember now we have two variables because we're looking at the correlation between x and y. So we're going to calculate the deviation score on x, the deviation score on y, and take the product of those and sum those products. That's the sum of cross products, or SP. So written out mathematically, for each row, I'm going to multiply the deviation score on x by the deviation score on y, and then I'm going to sum them. So here is the formula for sums of cross products, sum of cross products, excuse me. This is something that you should know and be able to calculate just off the top of your head. So now let's look at the formula for the correlation coefficient. Again, I'm going to do this two ways. First, the raw score formula. So the raw score formula, written in its simplest form, is just the sum of cross products over the square root of sums of squares x times sums of squares y. Remember, go back to the conceptual definition of the correlation coefficient. It's the degree to which x and y vary together, that's sum of cross products, relative to the degree to which they vary independently. That's captured by sums of squares x and sums of squares y. So hopefully you can see the concept there now that we're moving into the math. If I unpack that and write it in longer form, here's the sum of cross products, which we just saw. It's just the deviation score on x times the deviation score on y, sum them all. Likewise, we have sums of squares x, sums of squares y. Those are just the same old sums of squares that we did when we were calculating variance back in the summary statistics lecture. So now I can open up this formula. Here's the raw score formula again in its simple form, but now it's written out in long form. And I'm doing that because I want to show you that it's going to wind up being exactly the same as the z-score formula. But this is just the same formula written out in longhand. So this top part here, that's the sum of cross products. This part here, that's sums of squares x. This part here, that's sums of squares y, right? So these two are just equivalent. Now let's look at the z-score formula. I'm going to do the same thing, start with it in a simple form, unpack it, and then show you how it's the same thing as the raw score formula. So if we start with z-scores, remember any scale, any score can be converted to the z-scale and z-scores. So if we have everything in z-score form, then this is the formula for correlation coefficient. It's just the sum of the product of the z-scores divided by n. So again, now what I'm doing is unpacking that, writing things out in longer form. Remember, how do we get a z-score? Well, it's the raw score minus the mean divided by standard deviation. So that's just these first two lines. And then how do we get standard deviation? Well, first we can get variance. That's these guys. Right? It's the sum of squares divided by n, or mean squares. Then take the square root of that. That's standard deviation. So here's the final proof of equivalence. If I write the z-score formula out in really long form, then what I have is x minus m of x, so x minus the mean of x, over standard deviation written in long form. So this whole piece is just standard deviation of x. This whole piece is just standard deviation of y. Now let's write it in its really tedious long form. Again, this is just sort of packing and unpacking algebra. So if it's been a while since you've done this, maybe just review these slides a few times. For those of you who are really familiar with just basic algebraic manipulations, this this is review. But if it's been a while or if this is new to you, just review these slides. I promise you they work out, that they're equivalent. So now what I've done is this is a really long form. So what we have in the numerator is this whole piece is just z of x. I'm going to multiply it by z of y and just divide by n. That was the original formula in short form, right? Just z of x times z of y divided by n. So here it is again at the top. So this top part is exactly what you saw in the last slide. Now to go from this first piece here to this second formula, all I've done is, again, I've reduced some of the terms just by applying basic rules of algebra. So if you see in this top formula, we have n in both the numerator and the denominator. So those can cancel out. So we can reduce that formula at the top to this formula in the middle. And if you take a close look at that formula in the middle, it's sort of cool, right? Because it's sums of squares, or excuse me, it's sum of cross products in the numerator, and then sums of squares for x and sums of squares for y in the denominator, which, remember, is the raw score formula. So sum of cross products is right here. Sums of squares x is right here. And sums of squares y is right here. And remember, go back to the very beginning of the math segment. That was the raw score formula. So we started with the raw score formula in simple form, unpacked it, went to the z-score formula, unpacked it, and brought it all the way back to the raw score formula to show they're the same thing. They're going to give you the same exact number, the correlation coefficient. So finally, this concept of covariance is really important, and one that we'll use throughout this course, and something that you just need to have a fundamental understanding of to understand basic statistics. So just as in summary statistics, I emphasize moving beyond just measures of central tendency like the mean and embracing measures of variability like variance. Here too, you need to sort of push yourself to another level and say, okay, well, I know what variance is, but what is covariance? And you need to be able to just look at these formulas and, one, conceptually get them, and two, mathematically unpack them. So to recap, variance is mean squares because it's the sums of squares divided by n. It's a very simple analogy to covariance, right? Covariance, I'm going to just use COV for covariance, is the sum of cross products divided by n. Just instead of sum of squares, sum of cross products. And then correlation is just standardized covariance, so that the correlation coefficient fits between +1 and -1. In the same way that standard deviation is standardized variance. Okay? So variance to standard deviation is analogous to covariance to correlation. And finally, you might have noticed if you've been really sharp, we still have this issue of when to divide by n, when to divide by n-1. Again, this came up in the summary statistics lecture. If you're just doing descriptive statistics, technically the rule is divide by n. As we launch into inferential statistics, which will be next week as we start multiple regression, when you do inferential statistics, we're going to divide by n-1. And when we start inferential statistics in the regression lecture, I'll discuss that issue a little bit more. But for now, just if you're doing descriptives, divide by n. If you're doing inferential, divide by n-1. So to summarize, just know how to calculate this correlation coefficient. It's really important to know that math, just like you know how to calculate an average. It should be clear. Hopefully the concepts come through as you do the math. I've been teaching intro stats a long time, and a lot of students tell me that as they actually walk through the calculations for correlation and for even more advanced analyses, the concepts start to come through as they crunch the numbers. So if this is new to you or if it's been a while, challenge yourself and do it and review those slides. And again, the most important new concept is sum of cross products and covariance.